Hey, this is Chris Cow again. It's I actually just recorded a video yesterday on June 20th, 2018, but today's Thursday. I wanted to make a part two because just yesterday and today, because I recorded yesterday morning, it's just been mind blowing the amounts of things I've learned, and I just wanted to share and document the process. So some of the things I'll talk about in this video, I'll talk about a lot of things with the gazebo simulator, especially how I was able to create my own world modeled off of the actual lab hallways. I also talk about RQT graph and showing how all the nodes link up, which I learned a lot about. Also about some in the end I'll talk about some GitHub things. Also Hokuyo node, how that was set up, which was a pain. And yeah, the end some GitHub things that I've learned as well. So let's get right into it. So the first thing I want to show you is how I was able to create my own world. So this is actually in Sketchup, and with Sketchup, I was able to model out the hallways inside the Levine building at University of Pennsylvania, second floor. And I did this by having access to documents, which was already in the F110 Dropbox. So this gave me measurements, and I actually go out and measure some things myself, convert everything to meters, because Ross does a lot of stuff in meters. And I knew that each of these were like 5'4". They're actually more like 5'2", which is 1.5748 meters. And essentially was able to map out the basic structure in here. So this is super, super cool. I was able to map this out. It only took about an hour, and I ran into some issues. I'll tell you some of the tricks I learned along the way. But this is what it actually looks like when buying the gazebo. My wall following robot actually crashed here, so we'll look into that. Yeah, we'll figure that out. But what's really interesting here is just that there's no ground on the bottom because we actually load in the ground here. Otherwise, there's some physics problems because it uses it as a collision. And if we rotate down, I've made these about 1/2 meter tall. I didn't want them too tall. The robot only needs about 12 inches of barrier to see, maybe less. And these are important because we want to see if, as it comes around, if it'll go into these offices. They're actually rooms. The M lab is in the center here. And just super cool. I just basically traced out rectangles and just pulled them up. And that's essentially how it happened. So now that I showed you that, you can put the laptop away and show you the really cool stuff. So let me respawn this just so I can show you how this looks. So essentially what's really cool is that I have added in so last couple days I've written my own wall following because this is going to be used in the course. So we have our own F110 UPenn course repository, which is going to prepare students. It's like the reference code for the course. It's going to be a second-year master's level course, which is super cool because I'm not even in my second year and I might be TAing it. But here we have a launch file. So basically I added in a wall following, which is for simulator, and I even did a real world wall following. The wall following the launch file essentially calls the track Levine, which is a new track I created. And I actually forked the race car simulator by UPenn, which was originally from MIT, and added in the world, and it's public. And over here, I also allowed the robot to be controlled with the joystick, the Logitech F710, which I don't have right now. And these are the 3 Logix Python files, which allows to run it autonomously. And then this is real world following. I haven't yet loaded in the world. But what's cool, and this was added in just to get Hokuyo, which I'll talk about later. But essentially, this will do in the real world by launching MIT's Launch Teleop, which is super cool. So now that that's closed, let me show you how I run this. So of course, I've already done ROS core over here. And of course, I've also already done my source devel/setup.bash and cat can make. I actually learned today that I don't have to cat can make every single time, which is super cool. You don't have to cat can make when changing a world file or XML or Python. You only have to do when you change a C++ file. But I'm not really writing anything in C++ because I am scared of C++, to be honest. So I've just been writing Python, which is awesome. So let me run this. So here we go. It's launching this gazebo, loading in all the models. Here's gazebo coming up. It's gonna go full screen. And now you're going to see the model that I created, which is super cool. So if we look at it, here's a robot doing a simple left wall follow, trying to stay a distance of about, I think, 1/2 meter. This is actually, to me, it seems more than half a meter because the wall across is about 1.5 meters across. So I will need to figure that out later. But notice how when it comes here, there's the lidar. This part's white because it can't see that far. And it knows to turn itself, which is super cool. This is all driving by itself. I'm not doing anything. And because it's an accurate model, ideally once Jack gets the vest working, we can take this into the hallway and see if it works in the real world. Now, oftentimes things probably don't work well in the real world, but if this is a good enough model and the vest works well enough, then it'll probably work. Now here I've been having this issue where it keeps crashing to the wall all of a sudden, but I think we should be okay this time. Hopefully I can just do one lap so I can show you. But it's super cool to watch. I mean, this is literally going down. I want to wait till I get here just to end it so I can show you that it makes it past here. So I was super happy today. I was able to get this to work. I mean, Manas figured out a way to do a 3ds Max, but it's very daunting for me. I've never used it before, so I tried to find a very simple way that wouldn't take too long. I've actually done Google Sketchup back in middle school for a class I took in woodshop, but it's super cool. So here it goes. There's the robot. Here's a closer look. And what's really cool actually is if I pull up a separate window right now, I can actually show you what it looks like in RViz. So RViz will visualize the lidar scan. So watch this, by the way. Here's a robot. It knows not to turn left here. I honestly have no idea how it does that, but it's just cool that it does. So let me add RViz up here by topic to, I mean, you can tell I've definitely learned a shit ton of stuff in the last couple days. There's a robot. I think it's gonna crash. Oh shoot. Okay, it's gonna make it. This is what it sees right now, probably in disorientation. So you see that? This is what the robot sees. No, I don't know why, but it seems like one edge is longer than the other. Not sure why. Actually, it's supposed to go this way. It sees one wall is longer than the other, which is very confusing to me. But essentially, when I zoom out, there it is. Oh, it sees one is longer because of the fact that it's not perfect in the center. But this is super cool. I just want to show you. I mean, if it went this way, if you go into the Moore building, this would be the elevator. Because it's doing left wall following, it just turns left in a counterclockwise way. So this is super cool. I did not write the code for this. I did modify it and simplify it just to get reference code, but the bulk of it was already written by someone else. So I cannot take credit for that. But I did create this world, which is super cool. And I do understand the simulation a lot better now. Speaking of the simulation, let me just show you a couple things as well that I think are pretty important. I closed Gazebo, but notice how RViz is still showing right now. So I'll just keep that running. You can literally see the robot turning a corner right now. And I think it always crashes here. But it looks okay. Here it's literally printing out the PID, which is proportion integral derivative. And it's printing out the things about, for instance, here it's the current distance left and left is the future distance left, which I think is a little wrong because how can the current distance be 1.2 but future distance be 0.5? The reason it's wrong is, oh, I know the reason. The reason it's wrong, let me write this down, is that we're setting the car length as 1.5 meters when the car length is not truly 1.5 meters. So car length not 1.5 meters. Anyways, let me show you a little bit about the world file because it's super cool. So if I go back into my desktop, since workspace, and then it's inside source. Remember I told you that I had forked race car simulator, so it's inside of here, there's a world file. So these were all here, except I added the track Levine that world. Of course, it was based off these. And by the way, today I met this guy named Abhishek, who was from MIT and was a TA for the first course of the MIT race car, which all this is based off of in 2016, and he helped a ton. So shout out to Abhishek. But so basically here there's a ground plane. Abhishek's advice was to have a ground plane, and then on top of it, just put the walls. Not have a wall with the ground, because then you have problems with collisions and the robot would just go and suddenly like hit some invisible object. It was really confusing. Also, I had to set this to like -0.1, not -0.05, -0.1, just to move the z-axis down a little bit on the world. Otherwise, it was also hitting an invisible thing. The car's still running, by the way. You can literally see what it's seeing right now, but It looks like it went backwards or something. I can't tell, but it's cool. So anyways, let me check that off the box so I can get you the next thing to talk about. So there's gazebo. Let me show you a little bit of the RQT graph while this hasn't crashed yet. In fact, even if it does crash, it's not a problem. So I'm gonna quit RViz. So let me show you RQT graph, which is done using Ross Run. RQT graph, space, R, so I'm typing with one hand. All right, so this is gonna pull up this RQT graph, which will look a little daunting at first, but I'll walk you through it a little bit. It's really cool because you can literally see all the nodes and all the topics that are being published by Ross right now. And this is very powerful because then it's kind of like you're playing God. Not that that's great, but you know what I mean. So anyways, this is in the simulator. So essentially what we see is Gazebo starts it off. We have Gazebo, which has a simulated laser scanner. In the real world, it's not coming from Gazebo. In the real world, it's going to come from a laser scanner node. But here's a topic called scan. Gets the PID error, which calculates the PID error, again, proportion, integral derivative. This error gets passed as a topic to this control node, which then sets the speed. The control node setting the speed and turning then sends it as drive parameters, which goes to the sim connector, which, as the name is correctly said, basically connects the simulator, connects the parameters into the simulator. And normally in the real world wall falling example, this will actually, basically whatever things that are computed here will eventually get passed into the actual VESC, which is actually, I think, the same node or very similar. Wow, this monitor's getting pretty hot. So as you continue, all this doesn't make sense to me. Even like Abhishek didn't really understand this that much, but you can just trust that it works. Basically, there's a high level and there's a low level. And we want to show the low level when we want to see the velocity of the car. So if we want to see the velocity of the car, you're going to do a Ross topic echo on VESC / low level / Ackerman CMD mux / output, which then goes all the way back because it needs to turn the servos, but they're not actual servos, they're servos in Gazebo, so it feeds back to Gazebo. It's a loop. However, when in the real world, it's not necessarily a loop because once you move the car, the laser scan doesn't really depend on the car. The laser scan is something separate, whereas in this case, the laser scan actually depends on the simulator. So that's a little different there. If you have questions, feel free to comment below. So there's that. Let me check that off the list. Creating a world in SketchUp I basically talked about. I want to talk a little about Hokuyo, and if we have time, a little bit about GitHub, although I already said a bit about GitHub in terms of how I forked it right here. So Hokuyo is on now, which is super sick. So this is literally running. It's going through an Ethernet, because it only has Ethernet port, into here, and it gets power through this power board. Again, remember how we said that this thing, this transformer, transforms voltage to about 12 volts. These both output 12 volts, some of these output 8 volts, and it's basically running. And Jack, of course, helped me solder this power supply, so it just plugs into the wall, which is great, so we don't have to use a battery, because it only lasts a couple hours, especially so many things are plugged in now. Hokuyo's literally spinning right now. Can't really tell it's spinning. If I listen to it, I can trust that it's spinning. And so it's super cool. It was actually a pain to set up. So I still don't understand, but Abhishek actually really helped me set this up. So shout out to him again. So essentially what you do is when you go to, assuming that it already has its Wi-Fi connections, let me just show you some of my notes, just so I have this down. So this was actually some configuring the Hokuyo tutorial, but essentially it normally has the IP address, I think of, let me zoom in a bit, 192.168.1.15, I think. Essentially what that means is that for this Hokuyo node, this port has that 192.168.1.115. This has 192.168.1.11. It's just set. Maybe I borrowed this from the labs. Maybe someone before I really flashed it. You do something with Windows to change the IP address. Beyond my scope. But what I want to show you is that over Ethernet, if I look at the Edit tab, so basically, he did this. He had this IP address. Remember, this is what the Jetson sees it as. I honestly don't understand very well, but you can just take a look at it. Honestly, I need to brush up on it, and it's kind of like a one-time thing. But I believe this is the IP address of it, or this is the IP address of the Jetson, one of them. And it basically is like that. In the routes, you also need to check this so that it's not using this for internet. You want internet coming from the Wi-Fi. But notice how it's on its own subnetwork, 192.168.1.15. My router was originally also on 192.168.1 base, so I actually had to change it so it's based off of 2. So what does this mean? Well, it means that when I go to F1 LitLoft, which is my Wi-Fi, essentially, when I edit it, you'll see that the IP address, which is not showing up here, can I find it somewhere? Let me find the IP address for you. I have config. All right, so IP address is what? Ethernet 19, where is it? WLAN 192. It's on the 2 network. You see that? So now it doesn't work. Now it does work. Before, when it was on 0.1, also my internet actually wasn't working, which was pretty crazy if you think about it. So Hokuyo, in terms of getting that to actually show, I haven't actually done this yet, at least outside the lab. So let me actually show you right now, since we have a little bit of time left. Be a nice treat. So essentially, we're gonna have to do this ROS run URG node thing. So let me pull up this terminal and we're gonna type it in here. It's gonna be ROS run URG node and then the IP address is equal to 92.1. Okay, that's what I was confused by, because this is actually the IP address that it's saying. The 11 is what it's saying this as, and 0.15 is this, the Jetson. So that's why it made me a little confused when I was configuring Ethernet with 0.15. We'll figure that out. Anyways, it works. So I run this, right? And it's streaming data. So if I quit this side, and then I'm gonna open up RViz in order to visualize what the actual one sees. I hope I'm not missing a step, although I very well might be. So up here, I'm gonna change this to laser. Don't be shy. All right, I'm gonna add a topic, which is going to be by topic, laser scan. And once that's in, this is literally my room right now. If you look at my hand, look at the screen. Kind of. I don't know why it's like saving the data like that. I'm pretty sure that's just something we like do. But you basically notice as I move in front of it, it's giving this laser information. I honestly don't know why it's saving all the populated stuff. I'm pretty sure there's something to change it. But yeah. Okay, that's actually really weird. Huh. Anyways, you can see it's getting data. I know it's working in the lab. I'll figure it out later. Maybe it's in here actually. No, I already installed it. Basically all day just figuring out stuff like this. But yeah, it's super cool. The laser scan is working. So all I'm missing now is the VESC, which is actually back ordered. It's not going to ship till June 25th, which is like 4 days from now. And its price still backed up. Professional thinks it'll take 3 weeks. So we'll try and figure that out. For now, we use Jack's car to try and eventually early next week start actually running the car around using the wall falling algorithm, which is in the world. So then we're just using the actual world that it's simulating. So super cool. Hope you like this. More videos to come.